All right, so we have been dealing with gas laws. So we looked at Boyle's law, Charles' law combined. Now we're going to take a look at a different gas law or a different formula, and that's the ideal gas law. Basically, Avogadro said that equal volumes of gases contain equal numbers of moles at a constant temperature and pressure, and this is true for any gas. So what they did is they took the combined gas law and they also included the number of moles into that formula. So this is just like the combined gas law, it's just also including the amount of the gas, so the number of moles. So N is the number of moles. So knowing this information right here, what they did is they came up with a special number, which is R. Okay, it's a universal gas constant, and we use this in ideal gas law. And R is equal to 0.0821 liters times atmospheres over moles times kelvins. So it's a lot of units right there. It's also equal to this number if you're looking at kilopascals instead of atmospheres. But usually we do everything in atmospheres, so we can just stick with this one number right here. Now you don't have to memorize this. I will give you this constant. But let's look at how they actually solved for this number. How did they come up with R? Well, they said that you can include the number of moles into that combined gas law. So, P1 times V1 is equal to N1 over T1. Well, we know a few things. We know that at STP, 1 mole of a gas is 22.4 liters. So let's say that we are at STP. If we are at standard temperature and pressure, just looking at one side of the equation right here, we're at standard temperature and pressure, we are at 1 atmosphere. We are also at the standard temperature, which is 273 Kelvin. 73 Kelvin, sorry. All right, and we know that at STP, 1 mole of a gas is equal to 22.4 liters. Well, when you do the arithmetic for this, you get 0.0821 and then followed by all those funky units, atmospheres, liters, moles, Kelvin. That is how they calculated this number. If you're at STP, you know the volume and you know you have 1 mole of a gas. So that is how they calculated R, and this is also how they came up with the ideal gas law. Okay, they said that, okay, you have this number, R. That's R right there. So and that is equal to the pressure times the volume divided by the N divided by the T. So they rearranged this whole equation right here to say PV is equal to nRT. This is R right here. So this is our formula that we use for the ideal gas law. All right, enough of proofs. Let's go and do some problems. All right, so a container filled with 0.25 moles of oxygen gas has a volume of 2.35 liters at a temperature of 45 degrees Celsius. What's the pressure of the gas? So, pressure of the gas. First of all, notice that nothing in this problem is actually changing. That's why we do not use the P1 times V1 is equal to T2. We're not using the combined gas law here. Nothing is changing. Since nothing is changing, we're going to be using PV is equal to nRT. Okay, this is the equation we use if we are just trying to figure out what one of the variables is. If something is changing, then you're going to be using the other equation. So the first thing we're going to do, as always, is write down what we know. So the first thing, we have this many moles of oxygen, so N is equal to 0.25 moles. So N is the number of moles here. It has a volume of this. So the volume is 2.35 liters at a temperature of 45 degrees Celsius. So the temperature is 45 degrees Celsius. But again, we can't use Celsius here, so we're going to add 273 to that. So that's 318. All right. And we also know R. We will always know R. It will never be stated in the problem, though. And that's liters, atmospheres over moles times Kelvin. All right, we are looking for pressure, though. So we do not know P. So let's just make sure we have all the correct units here. Everything that's in this problem has to match up with these units. So we have Kelvin, so we're good on that. We have moles, so we're good on that. We have liters, so we're good on that. And we are solving for pressure, so we're going to solve for atmospheres here. All right, so at this point, all we do is just plug and chug. Hardest part is over. So we do not know P. All right, so at this point, all we do is just plug and chug. So our pressure, we do not know our pressure, so it's P times our volume, which is 2.35 liters, is equal to the number of moles times R, which is 0.0821 liters, atmospheres over moles times Kelvin, times our temperature, which is 318 Kelvin. All right. So I'm just going to make sure our units are canceling here. So moles divided by moles, that'll cancel. Liters will end up canceling once I move it over. Kelvin will cancel, so I'm going to be left with atmospheres. All right, so let's go ahead and simplify. So multiply everything on this side out. It's 0.25 times 0.0821 times 318. It's equal to 6.526. So let's get P by itself now. So in order to get P by itself, I have to divide by 2.35. All right, so we get 2.77 at the end. So just 2.8. And that's in atmospheres. All right, let's look at a different problem. All right, so it says 15.2 grams of NH3 is placed in an empty 2-liter container. The pressure is measured at 925 millimeters of mercury. What is the temperature of this gas? All right, so first thing, we're going to write down what we know. We were given grams. Now, we can convert grams into moles. So N is equal to 15.2 grams of ammonia. We're going to have to convert that to moles. All right, so 1 mole over so many grams, and this is the molar mass. So once I solve for the molar mass, I get 17. So I will have 0.9 moles. All right, now I was given 2 liters in a 2-liter container, so that is the volume. If you're ever talking about a container, that is the volume because the gas will spread out to fill that container. So the volume is equal to 2 liters. And I know it's volume because it's in liters. The pressure is measured at 925 millimeters of mercury. Let's look at R really quick, and I'll come back to that pressure. R is 0.02 or 821 liters, atmospheres, over moles and kelvins. All right, so my liters are fine, my moles are fine, I've already converted to that. I'm looking for my temperature right here. It's asking for the temperature. What is the temperature? Now, I do have a problem though. Pressure is given in millimeters of mercury, and I need it to be in atmospheres, because remember, everything has to match with that constant right there. So, millimeters of mercury needs to be converted to atmospheres. 1 atmosphere is equal to 760 millimeters of mercury. So that's going to be 925 divided by 760. So it's 1.217 atmospheres. All right, so now I have all my information. I just need to plug and chug. All right, so PV equals nRT. I know that my pressure is 1.217 atmospheres. My volume is 2 liters. My number of moles is 0.9. R is 0.0821 liters, atmospheres, moles, Kelvin. And I do not know what my temperature is. So let's go ahead. We need to simplify everything. 1.217 multiplied by 2 gives me 2.434. And I'm going to go ahead and just leave my units here right now so I can show you how they cancel at the end. So it's 0.9 multiplied by 0.0821. I'm just simplifying everything here so I can get T by itself. So it's going to be 2.434. Oh wait, no, I'm sorry. God. All right, so now I'm going to simplify. 0.9 times 0.0821 is equal to 0.07389. My moles will cancel right here, so I don't need to worry about that. So liters, atmospheres, over Kelvin. All right, so now I'm going to keep on moving. So I need to get T by itself, so I'm going to divide everything by 0.07389. Okay, so this ends up getting flipped, which will end up canceling this out, that out, and then you're left with kelvins at the end. So it's going to be 2.434 divided by 0.07389. So temperature is equal to 32.9 degrees Kelvin. All right, so just a reminder, remember an ideal gas. Ideal gases don't really exist, but we get pretty close to it. So an ideal gas has no attractive forces between the molecules. We consider the volume to be insignificant, so we say that it has no volume, but it does really have a volume though. And they exist at high temperature, so well above their boiling point, and low pressures.